Hello everybody, today we're going to look at inverses and determinants, and by the end of the video we should be able to determine the inverse of a matrix using our identity matrices and our determinants. Okay, looking at inverses and determinants of matrices. So first things first with our concepts, looking at inverse matrix. Okay, if I have K, now K is just some number, right? This is a non-matrix here, just a non-zero real number. Okay, the multiplicative inverse of K is going to be 1 over K, right? Okay, because if I multiply K times 1 over K, I get 1, right? So now in the context of a matrix, okay, if I have matrix A, that's an n by n matrix, okay, so that's going to be a square matrix, right? Okay, and then I have matrix B. Now if A times B equals B times A, okay, and that equals the identity inverse for however big for the size of this matrix, okay, then B is going to be the inverse of A, okay? B is the inverse of A. So how is this written? This is written as A, it kind of looks like A to the negative 1, okay? But it's said A inverse, all right? We say A inverse, but we write it like this, okay? All right, so let's take a look at finding the inverse of a matrix. Okay, so A is an n by n matrix again, okay? So first thing we're going to do is we're going to write an augmented matrix. We're going to have this, okay, a little bit different from what we're used to though, because I'm going to have A, my matrix, on the left-hand side, and I'm going to have the identity matrix of the same size as A on the right-hand side of that, okay? Then I'm going to perform row operations. So A is in reduced row echelon form, which we know looks just like our identity matrix. So if by the time we get done, I have the identity matrix on the left-hand side, then that means that A inverse is what I have left over on the right-hand side of the augmented matrix, okay? And if I can't reduce this to reduced row echelon form or my identity matrix on the left-hand side, then A is said to be singular, okay? Singular means it does not have an inverse. So let's take a quick look at this. Okay, I have matrix A here. First thing I'm going to do, I'm going to rewrite this as this is matrix A on the left-hand side, and this is the identity matrix for 2 by 2 on the right-hand side, right? Now, when I reduce the left-hand side, it doesn't reduce to row echelon form. So since this is the case, matrix A is said to be singular, okay? Now let's take a look at another one. If I've got matrix B here, okay, again, the first step, I'm going to rewrite this with matrix B on the left-hand side and the identity matrix for a 2 by 2 on the right-hand side. And if I go through my row operations and I get the identity inverse for a 2 by 2 on the left-hand side, then what's left over on the right-hand side is my B inverse, okay, my B inverse. Okay, and again, we need to check when we see this, okay, because when I multiply B by B inverse, that should be the same thing as B inverse times B, which should be, this is actually not 1, this is the identity inverse, or the identity matrix for a 2 by 2, okay? When I multiply those, they should be the same thing, all right? So now let's take a look at this concept of a determinant of a 2 by 2. Okay, so if I have matrix A here, matrix A is invertible meaning it has an inverse, okay? If AD minus BC, okay, so here's AD minus BC, it is not equal to 0. It's not equal to 0, and I'll show you why here in a second. Okay, but here are some ways that we write the determinant here, okay? And actually, this number right here, this is my determinant for a 2 by 2, okay? This number right here, this AD minus BC, or CB, okay, that is my determinant for a 2 by 2, okay? So make sure you write that down. This is the determinant. When we talk about determinants, we're talking about this number right here, or a 2 by 2. Okay, so if it's not equal to 0, then A has an inverse, and that inverse is the reciprocal of my determinant, okay, so 1 over AD minus CB. And then notice I've got my same matrix here, except all I did was I switched A and D, and then I changed the signs of C and B. Okay, switched A and D, changed the signs of C and B. Okay, and that, okay, I can multiply through by the reciprocal of my determinant, and that is going to be my A inverse. Okay, so that's for a 2 by 2. Now for a 3 by 3, it's a little bit different. Okay, denoted like this. Okay. Now my notes here on the left look the same, right? So DETA and what kind of looks like absolute value A, right? Okay, except now what we're doing here, okay, I've got A, B, and C, okay, outside of these 2 by 2 matrices. Okay. So when I look at A here, okay, what I'm doing is think about crossing out the row and column that A is in. Now what's left over is this 2 by 2 matrix EFHI, which is what I have here. Now I'm subtracting now B. When I look at B, I'm going to cross out the row and the column that B's in. Okay? And what's left over is DFGI, this little 2 by 2 matrix here. Okay? And when I take a look at C, again, crossing out the column and the row of C, what's left is DEGH. All right? Now what each of these is that we saw last slide, this is the determinant of this 2 by 2 matrix. So I have A times the determinant of this 2 by 2 matrix, B times the determinant of this 2 by 2 matrix, and C times the determinant of this 2 by 2 matrix. Okay, so it's a bit more of a process for a 3 by 3, but it is very much doable. Make sure you have that written down, and let's take a look at some examples. Okay, first example, we're going to determine if A and B are inverses. If A and B are inverses. If they are inverses, then we know that AB should equal BA, which is our identity matrix for a 2 by 2, which looks just like this. Okay, so let's take a look at AB. All right, we know the process of multiplying our matrices together, so I'll take a look at the first row times the first column first, and then first row times the second column for this element, and then second row times the first column, and then second row times the second column. Okay, that's our process there. I'll go ahead and erase that to clean it up. Okay, and when I do that, I am left with, oh, look at that. I'm left with the identity matrix of a 2 by 2. Okay, so now let's take a look at B times A. Okay, so again, B times A. Now I'm taking a look at the first row. Okay, so I've got 2 times. Now I'm taking a look at the first column. Okay, so 2 times -4 plus 3 times 3. Okay, and then I'll take a look at the first row times the second column now. When I'm looking at this element right here. So it's going to be 2 times 3 plus 3 times -2. And the same thing then when I look at my bottom row, first and second columns, how we get these two elements here. And when I start reducing those down, I get the identity matrix again for a 2 by 2. So A and B are inverses indeed, all right? Okay, now let's take a look at a 3 by 3, all right? Finding A inverse if it exists. Okay, so first thing I'm going to do, I'm going to write this out in an augmented matrix. Okay, again, I've got A here on the left-hand side, and I've got the identity matrix of a 3 by 3 on the right-hand side. Okay, so first thing I'm going to do, since I want this to be a 1, I'm going to go ahead and multiply this by -1. Okay. And then I'm going to say row 1 minus row 3, that's going to be my new row 3. All right, so that takes care of this 1 right here, makes that a 0. Okay, then I'm going to say -3 times row 1 plus row 2, that's going to be the new row 2. And that takes care of this 3 right here, making that a 0. And then I'll say 2 times row 1 plus row 3. That's going to be my next row 3. What does that take care of? That takes care of this 2 right here, this -2. Makes that a 0. Okay, so this is the matrix that I'm dealing with. And then I'll say row 1 minus 2 row 3. Okay, that is going to be the new row 1. And what that's going to do, that is going to get rid of my 2 here and make that a 0. And then I'll say row 2 minus 3 row 3. That's our new row 2. What's that going to do? That's going to get rid of our 3 right here and make that a 0. Okay, and then I'll say row 1 minus 2 row 2. That's going to be the new row 1. That's going to get rid of this 2 right here that we don't want. We want that to be 0. And I'm left with the identity matrix of a 3 by 3 on the left-hand side, which means that A inverse is what I have on the right-hand side. Okay, I was asked to find A inverse, so we can just rewrite the right-hand side as its own matrix as A inverse. Okay, now let's take a look at this one. Finding the determinant of the matrix, and then find the inverse if the matrix, if the inverse exists. This should be inverse. If the inverse exists, not the matrix. We know the matrix exists. Okay, so first we're going to find our determinant. Okay, the determinant again, AD minus CB. Okay, AD here minus CB. Okay, so A is 2, D is negative 2. So I got 2 times negative 2 minus C is negative 2, B is 3, or negative 3. Okay, so be careful with your signs here. But when I reduce this, I get negative 4 minus 6, which we know is negative 10. Okay. Now, if we were to do this the hard way, to find the inverse, we would set this up in an augmented matrix, and we'd go through the whole process of trying to get the left-hand side to be the identity matrix of a 2 by 2, and would be left with A inverse right here. Okay. But we have an easier way to do this. Since we know that our determinant is negative 10, I know that A inverse is going to be the reciprocal of my determinant times, okay, I'm going to switch A and D here, switching A and D, and then I'm going to change the sign of C and B. Okay, again, this is like my A, B, C, and D, right? So I'm switching A and D, so now I have negative 2 up here and 2 down here. And then instead of a negative 3 and a negative 2, I just switch the signs of those, okay? Just switching the signs. Okay, so here, now I just multiply through by my scalar, all right? And I've got negative 2 times negative 1/10, positive 3 times negative 1/10, 2 times negative 1/10, and 2 times negative 1/10. And when I reduce that, I get A inverse, which you can go back and check is the exact same inverse that we got on the previous slide, okay? And don't forget to check if I have A times A inverse, that should equal A inverse times A, which should be our identity matrix for a 2 by 2. Okay, but we're not going to do that for the sake of time in the video. Okay, last example, finding the determinant of the matrix, and then find the inverse if it exists. There we go, I got the prompt right that time. Okay, so finding the determinant first, then find the matrix, okay? So this one's a little bit more difficult because we have a 3 by 3. Okay, so again, finding the determinant. So first I'm going to look at A. Okay, when I look at A, I'm going to cross out the row and column that A is in. What's left is this 2 by 2 matrix that I have here. Okay, so now I'll take a look at B. So I've got minus B. Okay, so B is negative 2, so I change that to plus 2. Okay, so I'm taking a look at B here. I'm crossing out the row and column that we have there. And what's left is this 2 by 2, 4, 3, negative 2 matrix here. Okay, and then plus C over here for my last term, so plus C. Okay, so crossing out the row, crossing out the column, and I'm left with 4, 0, negative 3, 1. Okay, so what each of these little 2 by 2s is, it's just the determinant of those 2 by 2s. Okay, so I'll go ahead and find the determinant of each one of these. Okay, that's just determinant of this, and the determinant of that. Okay, that's what we have here in our brackets. All right. So when I do that, I get negative 1 times negative 3 plus 2 times 1 plus 1 times 4. Okay, so that reduces down, and I have a determinant of 9. Okay, and I'm not going to go through the whole process of finding this inverse. However, in another video, I will show you guys how to find the inverse using your graphing calculator. Okay, but until then, good luck on your practice.